Welcome. This presentation will explain distributed database using commodities trading and risk management systems to illustrate points made. First off, the difference between homogeneous and heterogeneous distributed database. Distributed database can be differentiated by the homogeneity or heterogeneity of their locally deployed database management system. Commodities trading and risk management systems, or CTRM, exhibit homogeneity or heterogeneity in their database management systems, or DBMS. Web-enabled CTRM using Oracle or SQL Server can implement homogeneous DBMS. However, CTRM with homogeneous DBMS are unlikely because such require common data schema, query language, and transact processing across distributed DBMS instances. CTRM with heterogeneous DBMS are more likely the norm, given the disparate nature of the industry and the business segments. Our next topic, shared characteristics of all distributed database management systems. All distributed DBMS share three essential characteristics: transparency in where data is actually located, transparency in how data is replicated to remote sites, and transparency in how data is actually partitioned and fragmented across sites, all with the objective of hiding the distributed nature of the database from users. Distributed database share other characteristics as well, including design and management challenges that distinguish them from the centralized DBMS. To illustrate, CTRM prioritize data consistency and timeliness, such as compliance and control capabilities that provide one version of the numbers across divisions, products, and geographies. CTRM will seek to hide implementation details underlying this business functionality, including the three transparencies expected of data, as well as systems level protocols and components. Specific resolutions depend on context and the company, but certain challenges likely receive common solutions, such as the choice of persistent messaging as opposed to the use of commit protocols. Our third topic provides examples of companies that would use distributed database. Glencore, Cargill, Nobel Group, the super majors in global commodities trading, operate in many business segments using complex processes, including commodities transactions involving global supply chains, material transformations, and hedging of financial risk. Super majors operate in an industry of unruly markets, yet require capture of vast amounts of data across regions and time zones to enable enterprise reporting and analysis. CTRM solutions of a monolithic nature are thus improbable. Planning of CTRM requires an architectural approach where functionality specific to commodities is provided within the context of an overall framework of data localization and enterprise consolidation. One such model suggests vertical silos of specific functionalities for commodities, cross-cut by common functionalities delivered either as centralized or federated services, thus capturing enterprise reporting, potentially in a centralized data store, while yet allowing federated risk management for local enterprises. Next, we consider factors most important to deciding to use distributed database as a strategy. The need to share data is the impetus, yet local autonomy, as well as the need for availability of systems and the need for speed of transaction processing are the essential factors driving the strategy. Cost and expediency also drive the decision, especially when companies or business units are already in operation. To illustrate, CTRM with distributed database provide autonomy to manage data locally, as well as to process transactions locally. though this autonomy is limited if the CTRM uses a homogeneous DBMS. CTRM with distributed database also afford faster transaction processing as remote network communications are eliminated, as well as improved availability due to data replication. Therefore, federated designs for CTRM afford these benefits while enabling enterprise reporting and analytics, and as such, are likely the preferred model for CTRM. Federated design also enables easier IT consolidations and capacity scaling, and as such are likely, again, the preferred model. Our fifth topic asks, why would an organization have a heterogeneous distributed database management system? The federated architectural model addresses the fractious nature of the global commodities market, as well as the supermajors' need for local speed and availability at their globally distributed sites. Local autonomy not only addresses concerns of local data management and transaction processing, local autonomy also drives the choice for heterogeneous federated design, as the model supports localization of data requirements and the distinct schema that such disparate requirements produce. Moreover, IT standardization and consolidation in this industry is challenging, and a federated, heterogeneous model facilitates easier pragmatic solutions. Our sixth topic contemplates the ease or difficulty of completely following CJ Date's rules for distributed database, specifically as they pertain to the DBMS and underlying technical stack. From a simple product perspective, enterprise-class products such as Oracle or SQL Server might be considered to largely comply, as they support a large array of hardware, operating system, and networks, as well as integrate with other DBMS, thus affording some of the independence expected by Date. From an implementation perspective, though, the systems level independence set forth by Date would be difficult to satisfy. Even if only a single vendor and its products were used, one is still challenged by endless minute considerations concerning hardware operating and network specifications. If two or more vendors are used, the contortions increase dramatically despite all enterprise-class DBMS essentially using the same architectural strategy, even with respect to how they connect to other DBMS. Our seventh topic asks whether any distributed DBMS follow all 12 of CJ Date's rules. One cannot assert, of course, that no such DBMS exists, but it seems unlikely. With SQL Server, developers struggle to implement Date's rules and cannot prevent some lack of transparency when databases are distributed. SQL Server uses server links and the SQL language to achieve language transparency, but it fails to provide resource access transparency from the developer's perspective. If comparing Oracle, designers of distributed database confront similar challenges. Oracle likewise lacks transparency in distribution. It cannot directly affect distribution as pertains to fragmentation and replication. From a purist perspective, then, these issues suggest even enterprise-class DBMS cannot satisfy all of Date's 12 rules. Our final topic looks to open source distributed DBMS and asks what are their features and usage. Blockchain technologies are open source distributed database, and their peer-to-peer paradigm in fact pushes towards the outer bounds of database distribution. Blockchain technologies, moreover, have several innovative features, including distributed shared rights without a centralized authority acting as trusted intermediary. Also, blockchains offer varying forms of immutable transactions, something unheard of in relational database systems. Financial institutions are especially interested in blockchain technologies, given the potential to simplify multi-party payment and settlement processes and more quickly close transactions. Yet blockchain technologies lack features common to database, especially relational database, and do not easily integrate with business applications. Their future, therefore, remains uncertain.